How Feynman discovered light that no one can truly explain. There is a strange irony in the story of light. It is the most familiar thing in our lives, and yet the most deeply misunderstood phenomenon in the universe. Every morning it wakes us up. Every night it leaves us in darkness. And every moment in between, it silently carries information from the distant stars to our eyes. Physicists have studied light for centuries, philosophers have written poems about it, and religions have used it as a metaphor for truth itself. And still, even today, no one can honestly say they understand what light really is. Richard Feynman knew this better than anyone. Feynman was not just another physicist adding equations to textbooks. He was a man obsessed with understanding, not memorizing. He distrusted explanations that sounded complete but hid confusion underneath. And when it came to light, Feynman reached a conclusion so unsettling that most people hear it, nod politely, and then quietly ignore its implications. He said, almost casually, that nobody understands quantum mechanics, and light is quantum mechanics in its purest, most unforgiving form. What Feynman discovered about light was not a single formula or experiment. It was something far more disturbing, that light does not behave like anything our minds are built to understand. Not a wave, not a particle, not even a combination of the two. Something else entirely, something only mathematics can describe, but no human intuition can truly grasp. To understand why this matters, we must first step back to a time before Feynman, before quantum theory, before anyone suspected that reality itself might be fundamentally strange. For centuries, light seemed simple. Isaac Newton believed light was made of tiny particles, corpuscles, shooting through space like invisible bullets. This made sense. Light traveled in straight lines, it reflected like a bouncing object, and it could be blocked. Later, experiments showed light could interfere with itself, creating bright and dark patterns that only waves could make. Thomas Young's double-slit experiment shattered Newton's idea and crowned light as a wave, spreading smoothly through space like ripples on water. Physics celebrated. The problem seemed solved. Then the universe laughed. At the beginning of the 20th century, experiments revealed something impossible. Light sometimes behaved exactly like particles again. It arrived in discrete packets of energy. It knocked electrons out of metal surfaces one at a time. No wave explanation could account for this. Albert Einstein explained it by proposing that light came in quanta, later called photons. Now light was both a wave and a particle. This was not poetic, it was a disaster. How can something spread out like a wave and yet arrive as a single particle? How can it interfere with itself and still hit a detector at a single point? Physicists invented language to cope with the contradiction, but the contradiction never went away. When Richard Feynman entered the story, the equations already worked. Quantum electrodynamics, the theory of light and matter interaction, could predict experimental results with astonishing accuracy. It was, and still is, the most precise theory ever created by humans. But Feynman was not satisfied. He noticed something terrifying. The better the math worked, the worse the explanations became. Instead of trying to force light into classical images, Feynman did something radical. He stopped asking what light is and started asking what light does. And what it does, according to his formulation, is something no human mind evolved to imagine. In Feynman's view, a single photon does not travel along one path from source to detector. It explores all possible paths, not metaphorically, literally. Every conceivable route through space and time contributes to the photon's behavior. Straight lines, curved paths, loops, detours, even paths that seem absurd. Each path carries a tiny arrow, a complex number, pointing in some direction. When all these arrows are added together, they produce the final probability of where the photon will be detected. This idea is called the path integral formulation, and it works disturbingly well. But what does it mean? Does the photon actually travel all paths, or is this just a mathematical trick? Feynman himself refused to answer in comforting terms. He insisted that asking for a classical picture was the mistake. Light doesn't owe us an explanation that fits our intuition. This is where Feynman's discovery becomes truly unsettling. When light passes through two slits, it creates an interference pattern even if photons are sent one at a time. Each photon behaves as if it knows whether both